to start a recording?
I am recording.
Perfect. All right. Well, thanks very much. And thanks everybody for your patience. So I think we are almost ready to get started. Welcome to everybody to this computing summer school hosted by ANITA, the Australian National Institute for Theoretical Astrophysics. Now, of course, we appreciate your patience with a summer school starting in June, but as some of you may have noticed, we've been going through a bit of a challenging time. We had been hoping that we might be able to run the summer school in person after all, hence the delay, but I'm hoping that it will work very well in this online format. So thanks very much for joining us. Let me just thank everybody who was involved in putting the school together, and in particular, Isabel Ramirez-Shaw and Greg Poole, who are members of the ANITA steering committee, have played a key role in this. And of course, we are delighted that Paul and Rebecca from ADACS are also joining. They are here online today, and they will be providing the tutorials for the next 2 Thursdays. But the plan for today is that we're going to have an introductory session to some of the opportunities for high performance computing available in Australia in the first hour and a half. And then we will have a little break. And at 3 o'clock Melbourne time, 3 o'clock AST, and 1 o'clock in Western Australia, we'll come back and we'll have a very exciting session that's going to be hosted by Isabel, and will include some very interesting talks and panel discussions on the overall impact of astronomy and astronomers on climate change and what we can do to mitigate that. But first, let me take this opportunity as the chair of ANITA. And by the way, I should have introduced myself. My name is Ilya Mandel. I'm a professor at Monash. But my role here is merely that of introducing the fantastic people we're going to hear from. And in particular, it's wonderful that for the next hour and a half, we'll have the pleasure of hearing from 2 fantastic speakers. We'll have Greg Poole, who is the ADACS coordinator based at Swinburne, and my colleague Bernhard Mueller, who is the ASTAC chair and is a faculty member at Monash. And without further ado, because if I started listing all of their accomplishments, we'd be here for the next hour. Let me turn this over to Greg and Bernhard.
Thanks, Ilya. Bernhard's going to go first today.
Yeah, I'm going to go first and then hand over to Greg, because that I think immediately connects to what we want to see. So yeah, thanks Ilya for the introduction. It's a pleasure to be here and tell the attendants a little bit about opportunities for supercomputing and hopefully efficient supercomputing. One of my messages is that I think the efficiency consideration is really the thing that you always need to watch out for if you want to be successful in supercomputing and actually getting resources for that. And that's, I'll give you some concrete advice on how you might go about this. There's not a huge secret art involved. It's just really very, very plain and simple common sense. But to really lay the groundwork for all of this, what I'd first like to do, is there a comment in the chat? Monitoring the chat.
Oh, sorry, Bernhard, that was me. I had failed in my duty to give thanks, and I just wanted to say that in particular, thanks to Astro3D for hosting the Zoom chat. Sorry about that.
To lay the foundations of what the possibilities that are actually there for you, I'd like to do a bit of an introduction into why we need supercomputing and centralized supercomputing resources at all, and then what ASTAC, the Astronomy Supercomputing Time Allocation Committee of Astronomy Australia Limited is actually doing in order to make such supercomputing resources available. And then we'll go into how you can actually get them. So, I mean, you certainly all realize that if you have any computing needs, right? Solving some equations. This can very quickly grow out of bounds, right? You start simple. The simplest way of doing computing is to do it by hand. Now, that's still possible nowadays in astronomy in some fields, but we all realize that in practice, we're working most of the time with computers assisting in our calculations. And these days, well, we all have our own computers available. We get them from the university. We can buy them ourselves, desktops, laptops, and that already gets us quite far. And you've probably done some tasks in that direction already. So nowadays, there's a lot that you can do on your own computer. You can run some simple simulations on your own machine without needing extra resources because the computers have become more powerful. We now have the multi-core architectures on normal user PCs and laptops. So you can already do quite a bit on them, but you will very soon get into the position that when you run, say, even simple simulations or do a simple kind of statistical analysis of data, well, the number of simulations that you do might grow, the amount of data that you have to process might grow, and then you might still be able to put that stuff on your own computer, but it would probably take you hours or days to run that on your own computer. So you need to at least use resources that can run in the background and maybe have more computing cores available to reduce the turnaround time to something which is reasonable. And usually, depending a bit on what institution you're at, usually you'll probably have some intermediate scale computing facilities available that can accommodate that. So your group might own bigger clusters, or your university might own some compute clusters that allow you to do modest scale jobs, maybe small multi-D simulations, maybe huge bundles of jobs that are otherwise relatively simple. But then for many of you, maybe not now, but at least in future, this will escalate to a point where the amount of time that a single CPU would need to execute your task would just grow out of bounds. If it's of the order of 10 to the 4 or 10 to the 5 core hours that you would have to spend, you have to go to bigger centralized resources. You need computers that have hundreds or thousands of computer cores available that work on this in parallel. For certain applications, the real bottleneck might also be just that the amount of data is so huge that you'd have to process hundreds of terabytes or petabytes of data. So especially if, now this is a theory school, but especially if you're someone working in radio astronomy, you'd be looking at inordinate amounts of data and really huge amounts of computations that you'd have to do. And that simply has to go onto centralized resources. And the key thing for those centralized resources, well, there are not too many such institutions available that can offer such big computing resources. The key thing there is that the way you get access to those resources is not simply by saying to someone, I need some time on a supercomputer, but because those resources are scarce, you actually need to obtain those resources in some kind of peer-reviewed proposal system. And let's go to what you can do about that in Australia. So in Australia, we really have multiple avenues available for you to get computer time in such amounts if your demands have grown to that point. And there are really two very different pillars. So we have on the one hand, access schemes for the big national computing centers. So for the NCI National Facility at Canberra, for the computing center at UHW UWA, PAWSI, and those national resources you can get access to by various national merit allocation schemes. So there is, for example, the most important one, that's NCMAS with annual calls, and you can get projects of, let's say, up to 20 million core hours per year. There are some more restricted schemes that only award a few projects each year and might be even a little bigger. And there might be special schemes, let's say, if you're working in a particular field that is that a facility is dedicated to, you might get preferred access to such facilities. For example, the PAWSI Center at UWA is specifically catering to radio astronomy. So there are additional means for you to get into some of those machines by that means. Or there might be sort of ad hoc calls or discretionary calls, directors' allocations, early adopter schemes that allow you every now and then to suck in some computing resources from these bigger national facilities. Now, the situation with the national facilities in Australia is, I should say, perhaps not everyone's aware of that. By international standards, what is openly available to the entire scientific community in terms of computing resources isn't actually very large. The facilities themselves are quite large, so they can accommodate quite a lot of computer time, but a lot of the computer time on the national facilities is actually handed directly to stakeholders. It's handed out basically by contract. So much of the machines may serve dedicated purposes already, and only a small fraction is really available to the scientific community in open calls. And of course, we as astronomers are only a part of the entire scientific community. So if you're going into the national merit allocation schemes, you'll usually be up against very fierce competition, and it can be quite burdensome to obtain the amounts of computer time that you might actually want to execute the simulations or the data analysis or whatever you want to do. Now, for this reason, Astronomy Australia Limited, which is an organization that really advocates for the needs of Australian astronomers in terms of infrastructure, be it observational infrastructure, be it membership in international organizations, and so on, participation in instruments overseas, be it equipment for high performance computing. AAL has made it, thankfully, its job to lobby for high performance computing resources for the Australian astronomy community and make some of that available basically by buying in buying resources on some of the big supercomputers that we have available in Australia, and also supporting dedicated facilities that are more geared towards astronomy. For example, AAL's putting support into the ASTAC supercomputer at Swinburne, and using those resources, you as astronomers, astrophysicists have some avenues of getting computer time in a somewhat more unbureaucratic process, depending on your needs. And there are really several tiers for that kind of access that could be of use to you. So it starts with a very low entry bar. So basically all Australian astronomers can get accounts on AusStar, the supercomputer at Swinburne, and do a little bit of stuff on that machine, at least enough to see that your code runs and prepare a bid for larger amounts of computer time. And then AAL is, through the Astronomy Supercomputing Time Allocation Committee, organizing two other proposal schemes. So one is the ASTAC schemes, which goes through 2 calls per year. So the turnaround time for getting computer time is much more convenient. You can get it on much shorter notice than the national schemes. And still, so the call volumes are limited. So in total, we hand out maybe a few million core hours in one such call, but it's still a decent opportunity for getting a few 100,000 computer core hours from a good proposal in a much less cumbersome way than going through the national merit allocation schemes. And since last year, we've also started to push for somewhat bigger projects. So since 2020, there have now been 2 annual calls for large ASTAC allocations where the individual projects alone already get several million core hours. Now, what I'm going to tell you is, in terms of practical advice, if you really find you need to go down the way of high performance computing, what I'm going to tell you in terms of practical advice is very much geared to how we're running things in ASTAC. If someone is already an experienced ASTAC user and thinking about now moving on to getting NC-MAS resources, they probably won't learn too much from this talk, but they don't really need to either. So this is really designed as an invitation for you to explain the process by which ASTAC hands out computer time, give you a few hints how you can succeed as a first step into high performance computing. So what we really want to do in ASTAC is, this is a program run by astronomers for astronomers. And this means that, and we also really have feedback from the community, which is, well, to some extent, because we are astronomers that actually run the panel, and we are astronomers who've put in our own ASTAC proposals in the past, or are still putting in ASTAC proposals. So we know what makes such an application process cumbersome or less cumbersome. And our philosophy is really not to put the bar too high. We really want a scheme that actually works well for astronomers, that is practical. We also specifically allow early career researchers to act as lead chief investigators, which is a nice opportunity for you to build a bit of high performance computing track record. It's a broader opportunity also to demonstrate some form of organizational leadership skills by being able to say, when you apply for a postdoc or a faculty position, yeah, you've run a number of high performance computing schemes which involve relatively complex tasks. So it's also designed as an opportunity for you to build your careers. And when you interact with the ASTAC team and also the ADACS team, which Greg will go into in more detail later, you'll find that we really want to be advocates for the high performance computing community in astronomy. We really want the projects to succeed, and we can handle things. We, of course, handle things by the book, but we can be a bit more accommodating. We can be a bit more proactive about making sure that the projects actually run, that computer time is used, will not be as punctilious about the application layout as the ARC, for example. So we might be in a position as a panel to seek for clarification if something's gone wrong during the submission of the proposal or so. So it's a much less intimidating application process than many of the other grant schemes that some of you might already be familiar with or might become familiar. Now, a bit about the major workhorses that we have available. So we usually allocate computing resources on the All-Star Supercomputer at Swinburne and on the NCI National Facility at ANU. In the last call that just closed a few days ago, actually, we also started to allocate some resources on virtual machines on the Nectar cloud. So there's a bit of variety in the kind of resources that you can get. I should also mention, for example, that both on OSDAR and GADI, we have nodes available, or sometimes many nodes available, that have GPU accelerators. And if you have codes that can use graphics processing units, this actually goes down very well and might put you in a good position to get computer time. So the machines are really good, they're well maintained, and they offer a bit of variety in terms of the specific requirements that your supercomputing codes might need. Now, about the structure of the application process and what needs to go in, which will then be followed by a few hints of what you or your supervisor, if you work together, should put into these proposals, what to put in and maybe what to avoid, what not to miss. So the calls usually take place in May and November. The application process is, by comparison, I should say, relatively lean. It has the documentation in total might seem relatively extensive, but it's really a process, an application process that you can complete within a few days. At the most, it's not a very onerous procedure. So the essential things that you need are science case, scientific justification, and that doesn't have to be very long. It can be 2 or 3 pages. That makes a good science case already. You'll need some bits of your track record. So things like publications, any prizes or so that you got. And you should not be intimidated by that. As early career researchers, I'll tell you in a few minutes what really counts there. And it's not that you have to be the Nobel Prize winning scientist in order to get computer time. We're looking for very specific things, and you have the best chances if you're a conscientious early career researcher who knows their stuff, who's up to speed on the technical requirements of what they're doing. That is really what we're looking for in the track record. And what is particularly important for the ASTAC scheme, and I should say probably for computing schemes in general, is the technical justification. What are you actually going to do? How are you going to do it? How many simulations do you need to run, and so on? That gets quite some emphasis. That's much more important than in other proposals to other funding schemes. So if you're asking for funding from the ARC, this would not nearly play the same role as in a computer time proposal. And if you're running an ongoing project, or your group is running an ongoing project, what we're also looking for, has that project been successful? So have you delivered results from that? Are publications at least underway and things like that? And I think I already hinted at that before. So in the ASTAC scheme, it's relatively easy to get decent computing resources, much easier than for the National Merit Allocation Scheme. And it's really a good point of entry for a scientific career in high performance computing. If you can demonstrate in a relatively lean and relatively application process in ASTAC that you can obtain and use computer time, that's a good stepping stone towards bigger projects in the national schemes. And it's relatively easy because of the current subscription rates that we have for the schemes. It's relatively easy to ask for a few 100,000 core hours and get all of that or most of that. Now, at some point, I mean, this is not going to be come relevant to you for a few months, but at some point, if people are going to do their own applications, what you'll eventually have to do is you'll have to go into the electronic online proposal submission system and basically fill in all those categories. And much of that is just Some of that is just administrative stuff, and it doesn't really make sense for me to go through all of that in detail. And I think I should just give you a few hints of what should be in your applications. So the science case is supposed to make clear the significance, impact, and innovation of your research and clearly state the aims. And I would also always say this is almost universally true also for other proposals, but you never should forget any of the three main pillars that you have, or four main pillars that you have for these proposals. You need the context, the big picture, but you also need to be very concrete about the problem that you actually want to attack. You shouldn't leave that open. You should be very clear what simulations you want to run or what kinds of data you want to analyze. That has to be very clear. The methodology should be discussed at least a bit in the science case as well. It's going to figure more prominently in the technical justification. And you should make it clear why the methodology is appropriate and competitive for what you're doing. And it's always very good in computer time proposals because they're not looking too far in the future. If you're very concrete about the plan of the work, the schedule that you want to propose, even check very simple things, right? So if you say, I'm going to run that many simulations on that many cores, well, how long is it going to take me to execute that? If you're asking for something which will, according to a simple calculation, take 2.5 years, and you're asking for that to be executed within a 6-month project, that's not going to work, obviously. And it's also advisable because computer time proposals very often face the challenge that the panels think many of them are fundable, they're good, but we just don't have enough computer time available to give away. So we're very often forced to cut the resources that we award. That's not always the case, but often. And in order to make it easier for the panel to say, well, we can live with a partial allocation, you might also clearly want to state that you can execute this project or meaningfully do something, even if you don't get all the computer time that you need. Yeah. Now, moving on to what you should put in as technical justification, and again, to stress the technical justification for high performance computing applications is almost, I wouldn't say quite as important, but almost as important as the scientific justification. So what you should always aim for is a breakdown of the simulations that you're doing, how much time they're going to take, how you're going to run them, how many cores, how much data are you going to generate, and so on. And the more detailed your estimate becomes, the more credible your application will be. That just conveys confidence that the person who's applying knows their stuff. Yeah. And if you can bolster that up also with, let's say, a few test runs. Yeah. This is what we do in industry with prototyping of new machines. A few test runs that benchmark the performance. So let's say, how much does one typical simulation take if you run, let's say, a dozen of them, and you can already say that, then that gives the panel good confidence that what you're proposing is feasible within the time frame of the project. So it's always best, but not absolutely necessary, if you've already done some tests, if you demonstrate that your code works on the target machine. But try to get there as close as possible, right? We're obviously aware that we can't ask for the simulations to be run already before they have been run. That's not useful. But try to go as far as possible in demonstrating that what you're proposing is going to work, is going to use up very close to the computer time that you request. What we don't want, and here it comes back, I come back to the consideration of efficiency. What we don't really want is we don't want resources to go unused. If we allocate computer time, it's always best if you can actually really use that.
Did we just lose Bernhard?
I think so.
Okay, let's give him a moment and see if he's able to reconnect.
Funny how things changed. If this happened during a live event, we'd be a little more alarmed, I think.
Perhaps, ever so slightly. You mean you're not in the habit of just falling silent mid-sentence in your live talks?
No, never seen it.
I wonder if people will start doing that now, in homage to Zoom. Even though I'm giving a live talk, I'm just going to pretend I have connection issues.
Because we're going to really miss it.
Precisely.
This is nostalgia. The young graduate students coming up 5 years from now will just not be able to relate at all. They won't know what they missed out on.
So let's give Bernhard another minute, and then maybe if if he's still having connection issues and is not able to reconnect, maybe Greg, would you be willing? I realize it's a little bit out of order, but would you be willing to do your presentation then, and then we'll have to
Sure.
make a break whenever Bernhard can rejoin us.
Given the nature of the stoppage, I bet you his laptop crashed. That would be my guess, because it just did that, didn't it?
Or his router crashed, or yeah, something crashed.
Might be a few minutes for him to reboot.
Let's hope it's not a meteorite that crashed into Bernhard. That would be worse.
It's not like the NBN to crash.
No, could never happen.
Yay, there he is.
Yeah, sorry, folks, talking about computing problems. So it turns out that my desktop computer just blanked out. I don't know exactly what's happening. But I'm actually quite close to the end. So I think I can just wrap up with some more hints. And I'll just offer to upload my slides later on. There's not really too much to add. I know what I wanted to talk about. So I should just say about the technical justification, be as concrete as possible in trying to say how your application is going to work. About the track record that you'll need for high performance computing proposals, I'll also be very brief. It's not that this is not a battle of bibliometric stats and citations. What we're looking for as ASTAC proposals, we're of course looking for whether you're productive and creative by the standards of your field. We know that the fields in astronomy work very differently, so we don't compare apples with oranges. But what we're specifically looking for is just people who know how to use their codes. Yeah, if you know about the algorithms that you're using, if you put effort into the application and making it readable and making it clear, that counts much more than a long track record of prizes and publications. And as early career researchers, you're at no disadvantage in leading those proposals if you have your supervisor backing you up. It's perfectly okay for early career researchers to go in as lead CIs. That does not affect the rating of the proposals in any manner, doesn't make them any less competitive. And I should actually say we've had a few success stories of people who've really done very well in ASTAC schemes. So for example, I should mention that this large ASTAC scheme, there we have one postdoc from ANU, Thomas Nordlander, who's been very successful and actually got those big allocations in the first 2 rounds, both of them. And I've personally been working with Jade Powell, who started as a postdoc at Swinburne and was very successful with ASTAC allocations. And now, partly because of that, not only because of that, but partly because of that, also managed to be successful with an application for an ARC DECRA, Discovery Early Career Researcher Award. So it's really relatively easy for early career researchers to get into high performance computing, do well in these applications, and use that as a bit of a booster for their career that you can use to demonstrate that you can coordinate relatively complex projects. So the supercomputing projects they're not cheap things. So if you have a project that's asking for 500,000 core hours, that's worth about, in terms of effective costs, about $20,000. If you're asking for a really big thing, 5 million core hours, that's worth about $200,000. So if you go into that HPC direction, you're actually managing relatively serious projects, and the people that have some experience with HPC know that and will certainly hold that to your in your favor when you're putting in applications for fellowships or jobs. And especially, and this ties everything back to the green computing theme, if you're contemplating, for example, getting involved at some future point in your career in meteorology, climate science, this is really where experience in HPC is a big asset, because those are the fields where heavy HPC use is certainly a major part of the game. And being able to use supercomputers efficiently and successfully is a good way of getting into that direction as well. And it's not very complicated. So if you just go to senior colleagues, ask for a look at past proposals, maybe, that's a good starting point. You just need to go really onto those bigger machines and get a startup account, which is very unbureaucratic. For that, you don't need proposals. You can get discretionary accounts on ASTAR and NCI for doing a little bit of testing. And then there's no black magic involved. So just taking some simple timings, running a few jobs, seeing how long they run, depending on the number of cores that you use and so on, that will give you enough data for a really strong technical justification and a good proposal. So it's not that you have to be a computer buff in order to be successful in high performance computing. It's very much its own thing. There's not really a big hurdle involved in getting started. You can become a very successful HPC astrophysicist within just a few, well, I wouldn't say a few months, you always keep improving, but there's not a big hurdle. And if you come to the point where the simulations or the data processing that you do is just growing out of bounds, it's easy to go in that direction. Also, the ASTAC panel will be helpful if there are questions about the application process and so on. And if you come to the point where you do test runs on a machine and you find the code just doesn't run, or if it runs, it just doesn't perform well, then the people on the help desks of ASTAR and Gadi will be very helpful. And if it turns out that you even need more support with making your application run efficiently, then you can go on and talk to someone like Greg after putting a proposal to get help. With that, I think I'm in a good position to hand over to Greg and talk about the ADACS application scheme. But before that, I should probably take a few questions.
Thanks, Bernhard. Any questions? Does anybody want to put up their hands to signal that they want to ask a question? We have a chat question
by
here.
Ben.
Yeah.
Yeah, this is, so whether there will be allocations through ASTAC on the new scheme, new machine at Palsy, that depends very much on the strategic decisions made by the AAL board. So whether they want to and are successful in buying computer time on that machine. And there's a number of considerations that go in that. The considerations are, how economic will that be? Do we get the service that people require, and so on? So I think I cannot really answer that at this point, but I can say that AAL is always very much eager to take the opinions of the community on board, and trying to, and is open to suggestions, and they're trying to do what they can to further the goals of astronomy. Whether that ends up in, the result is that a buy-in into the new machine at Palsy is a good idea or not, this is something that I can't tell in advance, really.
Any other questions? Yeah, I do want to echo a sentiment that I think Bernhard was really emphasizing, and that this is a kind of a very accessible opportunity for a lot of people in our community that is at times going underutilized. There's all these resources, both through these time allocation committees and also through ADACS, to really build up a track record. And the early career researchers among us, you should really be thinking strategically about how you can use these programs to demonstrate that you're kind of ready to manage larger projects, which is, of course, what people are looking for when they're evaluating ARC proposals. And you know, it's almost like the distance ladder kind of thing. It's the career, it's the career ladder, right? And this is these are the programs that are available to you now that you really should be thinking about, you know, thinking strategically about. And the longer you wait, of course, the harder it is to kind of formulate a plan around these things. Should be thinking about it right from the start. Okay, any other questions? I think, Bernhard, you might be back again at the end of the session.
Yeah, I'll try to be back as soon as possible.
There'll be other opportunities at the end to ask more questions. And of course, you can always email Bernhard if you have any offline questions. All right, shall we move on to the next speaker?
Good, I'll see you later.
The next speaker is Greg. So you almost get to introduce yourself.
Thank you. Okay, so let's see, how am I going to do this here? Can people see that?
Yes, we can.
Yeah, okay. All right, good. Well, thanks for the opportunity to speak today. As alluded to, I'm going to talk a little bit about ADACS today. And I feel like I've got one foot in two themes here. So the theme of this session is, if you will, sort of the opportunities that are available to you, the resources that you can exploit. But of course, the overarching theme of the whole school this summer is green computing. So I'm going to spend the first half of my slot here talking about ADACS, and I might move through that a little bit more quickly than I sometimes would. So, you know, there's opportunities for questions at the end if any of that I go over too quickly. And then the last half of my talk, I'm going to talk about ways that I think ADACS plugs into the issues of green computing. And I'm going to highlight sort of 3 things, just more or less off the top of my head, that I think kind of relate to the ADACS program in terms of green computing. So let me get this, there we go. So ADACS, what is ADACS and what are we about? So hopefully everybody here has heard of us. For those of you that haven't, ADACS has a vision of providing astronomy-focused training, support, and expertise to the astronomy community. Now that's a pretty broad mandate, but we have roughly 3 service components to the work that we do. One is training. The other is support for the ASTAC supercomputer that Bernhard was talking about earlier, and I want to emphasize that everybody here has access to that facility. If you find yourself slaving away trying to, shoehorn all your compute onto your laptop, you shouldn't be. You should be figuring out how to harness that resource to make your life easier. And the third component is a national support component. So here we have things like the ASTAC, supporting the ASTAC committee that Bernhard was talking about. We have a data management and collaboration platform where we can house sort of small to medium-sized data sets. We have an agreement with PASA, for instance, where small to medium-sized data sets that are referenced by their publications, they have an agreement with us where you can arrange to have those data sets housed in our database management system and have DOIs attached to them and things like that. But then sort of the main thing that we're probably known for in terms of national support is our professional software support program. So ADACS is divided between 2 nodes. So there's the Swinburne node, which I'm a member of. It's based at Swinburne in Melbourne, and it's principally responsible for software support work. And there's the Curtin node out in Perth, and they're principally responsible for training, but it's not a hard line. Swinburne helps with some of the training programs, and Curtin engages in software support work as well. So that's just sort of roughly a division of labor, but we try our best to work together to collectively support both activities. We commenced activities in March of 2017. So we've been going for, goodness, 4 years now. And much of our funding ultimately comes from AAL through an NCRIS allocation from the federal government. So I want to also highlight that at the Swinburne node of ADACS, we work alongside the Gravitational Wave Data Center. The Gravitational Wave Data Center started operations in July 2019, and it's roughly 8 to 9 FTEs worth of staff that provide similar sort of software support activities specifically for the gravitational wave community in Australia. We're supported by an advisory committee that sort of makes decisions about prioritizing the work that we do. There's 5 core projects: GW Cloud, GW Lab, Meartime, and GW Landscape are all basically web data portals, and Spear, which is a real-time sort of triggering code that sends triggers out when the LIGO observatory is operational. And GWDC also provides guaranteed time to the ADACS Merit Allocation Program, which I'm about to talk about, to gravitational wave researchers. And I encourage you to, if you're a gravitational wave astronomer and you haven't found ways of engaging in the resources that GWDC is offering you, go to this website and learn more, or you can email myself or anyone else in the team that's listed there to ask about how we can help you with your compute for gravitational wave science. So I mentioned the Merit Allocation Program and our national support, software support. So a lot of this is dealt with through this ADACS Merit Allocation Program. And for those of you who aren't familiar with it, I'll just go through it quickly. I want to emphasize that this is available to everyone here in this audience. If you're an Australian astronomer, you can be engaging in this program. We have 2 calls per year. The last one just finished, so the next one will open in another 6 months. But you can start thinking now about ways to engage this program. And it's all about getting trained software professionals to help you write and improve and extend your software code bases. So the way it works is we've tried to pattern it off. We've tried to, with everything in ADACS, we try to pattern ourselves off the cultural norms of the astronomy community. So the sensible thing to pattern ourselves off of here is a telescope proposal or a computing time proposal. The thing that is a bit different though is it's unlike a telescope proposal or a computing proposal. It's not fair for us to expect you to know how much of our time is going to be required for the work. So we front load the program with this expression of interest process phase, where we ask you to submit just a one-page description of the work you would like to do. Don't agonize over that. It should not be a barrier to entry. It's meant just to trigger a conversation with us. So we'll get that, we'll read it, and we'll say, okay, these are the two people who on our side who might be able to have an informed discussion with the science team about it. We'll arrange to have an interview with you. We'll coax out the technical details of the work. We'll develop an assessment. Once we agree at a concrete agreement of exactly what the work will be, we go and we develop an assessment of the amount of work that will be required. And then from there on, it's much like a telescope or like an ASTAC proposal that Bernhard was just talking about. In fact, you submit it through the very same system. And then much like ASTAC, goes on to an independent committee, and projects are awarded based on scientific merit and impact. Just to give you a sense of what we can do, the answer, is a bit, is kind of everything, really. We've got a very broadly skilled and diverse group of roughly 20 professional developers that we can call on to do work, covering the list of capabilities listed here. We've even entertained a proposal to do some IRAF work, which just is a bit crazy, but we almost did it. Just didn't get through the TAC, but we'll take on all comers, if you will. And that group is augmented by a suitable mix of skilled astronomers, so we can speak your language, we can translate what you're talking about into concrete software engineering practices, and as well as product discovery and delivery professionals, so we can ensure that the projects are managed professionally, delivered on time and on budget. When we do things like when we do web development, we can make sure that the web applications that we build are developed to a professional standard and all that sort of stuff. Here's a list of all the projects up until last semester that have been supported by the allocation committee. And you can read the titles here. You'll see that it ranges the whole range of science cases, but color coded here just in terms of the type of work. And the point I'm just trying to make here is the diversity of the work. So there's web applications, there's CPU optimization projects, there's GPU optimization projects, and a mobile app that we've worked on, database optimizations, you name it. So just about everything. So if computing is part of your work, and I assume it probably is for everybody in this audience, and if you would like your code to work better and faster, which I assume applies to everybody in this audience, you really should be thinking of ways to engage us and use us to further your science programs. I also want to emphasize that we're now taking training proposals to this program as well. And I can give a whole talk about the philosophy behind this, but I'm really excited about this. So if you have some sort of training need in your group, like let's say you've got 3 or 4 graduate students that are contributing to a code base, and they're all sort of stepping on each other with their commits to a Git repository, or the Git repository is in such a mess that they're all just working independently, and everything's diverged so much that you can't even harmonize the code base anymore. Or if you know that you've got a little bottleneck in your code, and if only you could get a little bit of help with how CUDA works, you could CUDA optimize some little bottleneck in your code and extend your science program. et cetera, et cetera. If you have anything like that, that you can imagine a bit of training would help you with, please think about writing an ADACS Merit Allocation Program training project, and we will parachute into your group, develop training specifically for you, and deliver it specifically to you. And you know, the list of other training activities we engage in is given here. So face-to-face workshops, you know, so you'll see that with Rebecca and Paul in the next 2 weeks. They'll be engaging in face-to-face workshops with you. We have a learning management system that hangs off of our homepage. So if you go to the ADACS homepage, you'll find a learning management system there with material about how to use Git, how SQL works, what HDF5 file format is and how to use it, et cetera, et cetera, et cetera. This is a particularly good resource, I think, for new graduate students. So I encourage supervisors of graduate students, whether you're postdocs or faculty, if you're managing graduate students, one of the first things you should maybe think about doing is sending them to this learning management system so that they can get a 101 level rundown on the sort of technologies that they're going to encounter in their research careers. Some or most or maybe even all of that material is hosted on our YouTube channel. So if you just search ADACS Learning, you'll find that. We host all the code that we developed through GitHub, and as a matter of principle, everything is open source. We run an internship program and we curate other online resources. So that's my rundown of ADACS and what we do. I hope that wasn't too quick, but if you've got any questions still, we can talk about them at the end. I now want to just take a little bit of time to talk about 3 ways that I think ADACS sort of touches on the theme of green computing. And again, these are just random things off the top of my head. I'm sure there's others, but this will hopefully at least stimulate some thinking and maybe stimulate some conversation. So 3 themes. One thing that I would assert is that professional oh, did I get muted somehow? Can people hear me?
Can hear you now. We did lose you for a second. Yeah.
Sorry, not sure what happened there, but you seem to be okay.
Okay. So did you hear me up to the start of this slide?
Yeah.
Okay.
I think we only lost like 5 seconds or so.
Okay. All right. Okay. So my first point that I'll assert on this theme is that professionally developed code helps eliminate useless compute. And by useless compute, well, I'll go into that in a little bit more detail in a bit. That data portals, so these would be like web applications, help eliminate redundant compute, and I'll provide some anecdotes there and to flesh out exactly what I've got in mind there. And that software optimization is about developing new capabilities, but the conversation I'd like to kind of see there is the kind of new responsibilities that come from new capabilities and being able to run on larger systems. So this first issue, professionally developed code eliminates useless compute. So I think hopefully this is sort of manifestly obvious, but I'll talk a little bit about it from my perspective. So if your code is, so properly professionally developed code, one thing that is a staple of professionally developed code is that it is well tested and that it is formally tested. And ideally, there is a test harness around the code base, which is being run at a very high cadence. So as you are making small changes to the code, hopefully a professionally developed code base will have a test suite that runs quickly, and you can check as you're changing the code base if you're breaking any previous functionality. So hopefully this has been demonstrated and it's manifestly clear that this leads to more reliable code, and that hopefully this leads to less loss to flawed execution. I can give anecdotes from my own research career, my old sinful days as a cosmological simulator. There were certainly numerous simulations I did that basically just had to get thrown away because of just mistakes in the code. You know, a variable that was cast as an int that should have been an int 64, for instance. And so a number overflowed, and, you know, it looked fine on all the little tests I did, but it wasn't properly tested. And when I extended the code, it broke. And so I ended up having to basically throw away a large simulation. If I had a proper test suite around that code base, I can certainly remember instances of things that really should have been caught if the code had been developed professionally. But of course, as researchers, we're not paid to develop professional code, we're paid to do science. And so in our rush to get to the science, we sometimes are a bit wasteful as we stumble through our work. Also, professionally developed code is easier to extend and refactor. So you end up losing less compute to wasteful debugging cycles where you're just wastefully and very inefficiently debugging your code. Maybe there's an error after the code runs for 10 minutes and, you know, you've got to run it for 10 minutes every single time with print statements to figure out what the problem was. And you do that 20 times, and a properly developed code with unit tests, for instance, might have been able to catch that mistake in seconds. It's also easier to build communities around professionally developed codes. And the idea here would be that, you know, often I think there's a lot of students that are writing codes that have been written by 100 graduate students before. And it is just all the effort that goes into developing that code base. Well, it's educational for the graduate students, not a total waste. But in terms of compute, and this issue that we have before us here in terms of reducing our compute, it can be quite a wasteful exercise having all these, you know, pipelines and simulation codes that really are all doing the same thing, and all the effort that went into developing them was wasted. So that's what I mean by useless compute, that properly developed code. And that's what ADACS's mandate is, to help the community adjust its practices around computing and bending towards more professional practices. It's one thing that we can help with. Data portals and how they can eliminate redundant compute. So I'll share an anecdote here. I was having a bit of a chat with Paul Lasky and Eric Thrane yesterday. It just in time for this talk. It was perfect timing. So they were relating to me that they've got a colleague at Monash, Avi Vejpayi. I hope I'm not totally getting Avi's last name wrong. Avi has been working on a paper, and what they've done is they've taken like a large number of LIGO triggers. I don't know if it's all the triggers or some filtered subset of the LIGO triggers from the last LIGO run, and they've run suites of inference jobs on all of those triggers, trying to see if they can detect some signal that's really down in the noise, basically. And they estimate that they produced 167 tons of carbon from 1.3 million CPU hours of compute from that work. And they estimate that 80 to 90% of that compute had already been done by the community. When LIGO was announcing triggers and releasing data, every researcher and their dog would stampede off and do their own analysis. And that community is really quite organized around tooling, and a lot of them are using the same code base called Bilby, which is a code base developed at Monash for doing a lot of that work. And a lot of them are doing identically the same calculation. 200 to 300 gravitational wave astronomers in the parameter estimation group, hundreds of astronomers doing exactly the same compute on exactly the same thing. And this is a complete waste. And you see the amounts of carbon that are being wasted just from this one application. So one of the things we're doing as part of the Gravitational Wave Data Center is developing a tool called GW Cloud. GW Cloud allows gravitational wave researchers to run inference jobs just through on LIGO data streams, just through a simple web application. So you can log on here and you can see, you can select the detectors that you want to have involved in your analysis. You can set the parameters of the of the inference calculation that you want to do, and it'll go away and it will launch that job on the ASTAR supercomputer or on the Caltech infrastructure. And that result, so and then the researcher comes back, checks to see if the job is done, and then they can kind of look at the results through this web application. And they can also, though, there's lots of reasons to do this, lots of reasons that are science-based for doing this, but there is one very conscious payoff from this, where they are very conscious of the fact that there is a chance here to really save a lot of wasted compute, both in terms of the money that's wasted, but also in terms of the carbon footprint of the work. So one thing that they intend to do with the system is make this the de facto repository for accepted runs that have been done on LIGO data that are the result of published works. So a published work that does a Bilby run can deposit that run on this system here. Researchers can either download the job through the web portal, or they can write scripts and use an API that we're developing. This API, this example here, you get an authentication token from the web portal. You drop that in here for your particular user account, and you can pull the system. You can query for jobs, and then you can do things like print the jobs or do analysis on the jobs. So there's an example of how a data portal can. Sorry, I got a delivery man at the door, but I'll just let him go. There's an example of how data portals can reduce redundant compute. And the role that ADACS plays in this is that building a web portal isn't something that's naturally within the means of a science group. Not only does it take a lot of time and effort, but the skill set of web development is really quite different from the skill set of scientific computing. And so we then have a group of trained professionals that can do this work for the community. It's all about organizing, though, as a community and agreeing that these things need to be done. So in terms of, and then the last theme I wanted to touch on was this theme of software optimization and how it can build new capabilities and new responsibilities. So I was lastingly affected by a talk I watched on YouTube quite some time ago by Linus Torvalds. And if nobody's actually seen this talk, he's at Google and he's giving a talk about Git. And it's worth watching just for the entertainment factor, because if you've never seen Linus Torvalds, who's notoriously the original developer, one of the original developers of Linux and its name, but also of Git. If you've never seen him give a talk, they can be pretty entertaining. He is quite cantankerous. There's lines in the talk where he says, if you're not using Git, you're ugly and you're stupid, things like that, all tongue in cheek, of course, but it is an entertaining talk. But he makes a point towards the end of that talk that has sort of lastingly stayed with me, where he talks about, he says, the only thing that matters is how fast you can merge. And he goes on to talk about, if you can merge quickly, you can do other things, like you can do diff checks and make sure you do integrity checks of the code, of the repository. And that quote, this is the kind of performance that actually changes how you work. So the point being made here is doing things faster isn't just about doing more of the same thing. That sometimes when you can do something faster, you open up a whole new capability that you didn't have before. And that is really what's, which is, in the best sense of our drive to bigger computers and running bigger simulations, what's really ultimately lying behind that is we're building bigger systems and running bigger simulations where we're accessing new physics, we're doing things that we couldn't do before. And I'll give just a couple of quick examples of ways that ADACS has been involved in this. This is an example of Rory Smith, who won an ADACS Merit Allocation Program project to optimize a gravitational wave waveform generator that was used. It's used not so much now, but it was used quite a bit when the proposal went through. So this is an example of strain as a function of time from a coalescing binary. And we GPU optimized that code. And you can see that in the regime where they do a lot of their science, we managed to, with just a couple months of work of one developer, achieve something on the order of magnitude speed up. Now, that doesn't just mean that they do their science in 1/10 the time and they can go and sit on the beach, although I guess they could do that. It means that they can do things now that they couldn't do before. Now they can build these models so quickly that they can do things like they can do inference, and they can run Monte Carlo Markov chain calculations on events, for instance, which is maybe something they couldn't do before. Or instead of agonizing to wait for one inference on one event to happen in 10 days, now it happens in 1 day, and they can do statistical samples of inferences on events. And of course, this is a concern for them as LIGO goes into 04. They're not going to be dealing with hundreds of thousands of events. They're going to be dealing with tens of thousands of events. And being able to chew on all that data is going to be quite a challenge for them. Another example of Bernhard, who you just saw give a talk. So Bernhard doesn't just evaluate proposals, he also writes them and is awarded them. So this is an example from last semester where he won some time for us to take a sort of a proof of concept 60 Boltzmann solver that he had that just ran in serial on one core, and to NPI it so that it could be run in a distributed way. And we've sort of done that now, and this is showing that this code can now be extended to hundreds of compute cores. And this paves the way now for the very first multidimensional supernova simulation with Boltzmann neutrino transport. So this is a whole new capability that didn't exist before that optimization has brought. So ADACS, this is sort of bread and butter work for us. But I just want to also, and this is good, this is the way new science gets done in our community, and this is a big part of what we do. But I think it is in this in this forum that we're in over these next few weeks talking about green computing, to meditate upon, I think it is prudent to meditate upon the fact that this is kind of built in to how we operate. We're optimizing codes so that they can run on these larger and larger systems, and we can get more and more of these large programs through larger and larger systems. But it does sort of drive demand and increase the consumption of compute. And so there is the side of the green computing discussion about making sure that the energy that we're consuming is sourced sustainably and appropriately. I think it is beholden on us to really think deeply about ways that we could be fighting against this drive to always consume the new resources that we get, and ask questions, how should we or how can we organize as a community to manage this? So for instance, cosmological simulations, does every researcher need to run all their own cosmological simulations? Can we as a community organize in sensible ways where peak facilities are running just a small set of large simulations in service for the whole community? Now this requires the community to organize in ways that I think maybe we do to some extent now, but perhaps could be done far better in the future. So I'll leave it there. Those are the points I wanted to make, and hopefully there's still a bit of time for questions.
Thank you very much, Greg. And there's a hand up from Adam. Adam, go ahead.
Hey, Greg, really well said, especially at the end there. So as you were describing things that are appropriate for ADACS, I definitely had a moment of, oh, you are describing the exact situation I'm in. So you've convinced me I should apply for time, or yeah, apply to get help. I was just looking on the website. I see that there was a call that was due at the end of last week. How hard is that deadline?
Yeah. Well, it's a very timely question. So we are changing things up a little bit. There will be an announcement coming out, I would say probably early July. And we are going to be starting to do a code audit process on a rolling basis. So the EOI phase right now, as it stands, starts about a month before the proposal deadline. And what we're going to do now is just make the EOI process a rolling, continuous process. So, you know, from July forward, keep an eye out. There'll be an announcement and we'll say, okay, come to us with your problems and let's start these conversations now. And we're going to set aside some resources because it can take a bit of work. You might come to us and say, oh, I've got this code base. It's just not, you know, it's just grinding to a halt when I run it on more than 10 cores, say. And so it's a fair bit of work for us to go profile the code. Maybe you do, maybe you don't know how to profile the code. If you do, that's great because that gives us, you know, allows us to really accelerate the process of figuring out what's going on. But maybe we need to profile your code. We need to dig into it. We need to look at the technologies that are being used, think about what could be done to mitigate the problem. And it is a bit of work. So what we've done in the past is you apply for time and we've had a fallback where the TAC can award what we call a code audit. But then the problem is we do that work and then you got to wait 6 months to reapply. So we're hoping that this rolling EOI process now will sort of reduce the latency between you engaging with us and you really getting the kind of help that you need. So just keep an eye out for that announcement after July. Does that answer your question?
It absolutely does. That sounds very sensible to me. Thanks a lot.
Okay.
And Aman has a question.
I really loved your talk, but like, I have a question which is not about the optimization that you're doing, which is like excellent, but how much of an effect do you think it could have if you start training new researchers to write better code from the beginning?
Oh.
Because I know that when I look at my old code, I kind of cringe and I'm constantly teaching myself.
Yeah,
so
absolutely. I think the problem cannot be solved by us parachuting into everybody's research program and writing their code for them. It's just too big of a problem for us to ever really fix the issue that way. I think we really, particularly with the fact there's a whole new cohort. Most of the code, let's face it, most of the code in this community is written by graduate students and postdocs. And there's a new cohort of graduate students every year. And we're only going to really make sizable inroads on these problems by teaching the community how to do it right at the first step and being there to hold people's hands through the process and to change the cultural norms of the community. So I see ADACS, yes, we've got developers that do concrete things and solve concrete problems, but I see ADACS really as much or maybe even more as a cultural exercise. We need to shift the culture of our community towards more professional standards. And the only way to do it is through training. Yeah, and that's part of the reason why I'm excited about the merit allocation program training program, because we really want to get in with groups and see what the issues are. We want you to tell us. We could imagine what's needed for training for the community. We could do like a 101, you know, introduction to Python. We could run that program every year. And, you know, and we do at some level do that, and that is time well spent. But I think we're only really going to get to the nut of the problem with the cultural issues of our community around this by really getting in and intimate with the science teams and getting close with you and sitting down together and working through this and trying to do that with as many groups as we can and try to build up a picture of what those cultural issues look like to understand how we can best help you. So I am imploring the community to engage the merit allocation program training, the training aspects of the merit allocation program, because this is the way we're going to build a better understanding of how we can help graduate students and postdocs to do it better from step one. It also makes our life easier, because then when we ultimately do when you ultimately do get our time to help optimize your work, we're starting from a much better place as well.
Can I just follow up a bit? So while you're doing this and as you work on projects, I think it might be helpful if you start writing down common problems and common solutions and maybe putting them on a GitHub repo, like this is the kind of testing standard you should have. And then people are interested in improving their code. They have a place to look and say, this is the standard you would like or would be ideal. And these are resources where you can teach it to yourself.
It's a good suggestion. And we are trying to work towards that. It's a bit of a slow process, but yeah, we certainly want to be able to provide those sorts of things for you.
Thanks a lot.
Are there more questions for Greg? Greg, since we have a couple of more minutes, maybe I can ask one while we're waiting for more questions. So I really liked your I liked all of your talk, but I particularly liked your last slide. It was very thought-provoking about what happens. Of course, as the codes get better, we just want to be able to do more with them. It doesn't necessarily mean that we stop running the codes. I'm not completely convinced that we can just say, okay, if somebody has run this code, or not this exact code, but rather written and run a similar code at some point, because we are, if we think of a code as a kind of numerical experiment, right? Just because somebody measured the value of big G doesn't mean that people will never try to measure the value of Newton's constant again. In fact, they do continue to measure it and look for either refining it or looking for deviations, etc. And and that's sort of normal and healthy, right? And people make slightly different assumptions. And somebody wrote a cosmological simulation, but I don't quite think that they made the right theoretical assumptions, and so I might want to run my own, for example. But I do wonder if maybe we are, as a community, misled in some sense by feeling that computing is often free to us in a way that building an experimental kit is not, right? So if somebody tells me that, yes, sure, you can do your own big G experiment, but it costs you $10 million to buy the necessary lab equipment, well, I'll think twice about it, or at least I will be forced to come up with a damn good reason for a funding agency to give me that $10 million to be able to argue why I might see something different or get a better measurement, right? Whereas in a way, it's nice that I can log into a cluster like ASTAR, for example, and not really have to prove my worth or the worth of my code very much before being able to burn some computing cycles on there. But is it worthwhile to increase both the awareness of the cost, in the sense that maybe if I'm applying for time, if I should actually be told, here is how many carbon how many tons of CO2 you're going to even if the time is free for you, this is the damage you're doing, or the electricity you're burning, you're using, etc. And also maybe some kind of a greater awareness of indeed the responsibility to at least not waste the hours. What are the simple checks I must do to convince you to allow me to run my code in ASTAR, in terms of showing you that I've at least done a minuscule amount of effort to optimize it, for example.
Yeah, I can. So if I understand correctly, I think there's essentially 2 points you're making there. One is the issue of compute as numerical experiments and how it is important to have more than one experiment, and that's an important part of the scientific method. And I completely agree with that sentiment, and I didn't want to suggest otherwise. But so just drawing from my own personal experience as a cosmological simulator, an example there would be the Eagle simulation versus Illustris, right? They're two very, 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 very expensive calculations. run with different codes, and they generate, you know, similar but different in very interesting ways results. And that is important to the science that's being done by that community. So, but it's all about just striking the right balance. I will, on the other hand, though, just from personal experience, I just know there are thousands of cosmological dark matter simulations that have been run that surely didn't need to be run. I mean, I would have run a lot of, I'm part of that. I'm sure they're, 125 megaparsec box with 1,000 cube particles. That's been done how many thousands of times, and how much carbon's been generated because of it. So it's all about getting the balance right. And I just think the community could maybe be organizing around that a little bit better. Next, and then in terms of the compute being sort of almost invisible, I think you were making a point along those lines. Agree. I don't really know. I mean, we think well, I guess we're charged for the electricity we use in our homes, so that's a way that we're made aware of it. Should we expect all researchers to publish right before the acknowledgements on their paper how much carbon was generated through some accepted methodology, how much carbon, and just make it public? Could we just publicly shame people? It's just one idea off the top of my head. I don't know, but we need to think about ways of doing this, don't we, to kind of drive the demand down, as well as to source the supply in a more sensible way.
I think it might be almost the perfect leeway to our next topic, which we'll get to after a little break. But I think first there was a question from in the chat window for you, Greg.
Look here. This might be more, I'll just read it out. This might be more specific. There was a mobile app developing project. If it's okay, I would like to hear more about its motivation, objective, and the end product. Okay, so that is a group based in Poland called Credo, and they have a citizen science project where you can, if you've got their app running on your cell phone, you can put it face down, and the CCD in the camera acts as a cosmic ray detector. And it picks up events, and then it sends triggers back to their database, and they can correlate events that they detect across the world. So they're trying to pick up these huge mega showers where there's like these extremely high energy cosmic rays that come in and create showers, and that shower just goes right through the Earth. And they are correlating events picked up on different cell phones across the Earth. So what we did is they had an app that was a bit rickety and running just on Android, and we developed an app using Dart and Flutter, which is a cross-platform web language that allows you to develop an application that just works on all mobile platforms, so Android, iOS, and I think even smart TVs. I think Flutter even works on smart TVs. So yeah, so we refactored their app in Flutter, and we've got it pretty much done and working now. The issue that we ran into, though, is that modern cell phones, the Flutter APIs only access sort of a cleaned version of the camera APIs, and I think on chip they remove cosmic rays now. So the hardware is starting to filter out the cosmic rays. So there's a bit of work that still needs to be done to access a version of the images that haven't had the cosmic rays cleaned. And that's sort of code for the science teams to worry about. But we've basically got the problem down where they just have to kind of figure out how to solve that little problem. Does that answer the question? Yeah.
That's very cool indeed. Are there any last questions so I see that Bernhard has also rejoined us. Are there any last questions for either Greg or Bernhard? If not, I suggest we take a break for 25 minutes, stretch your legs, arms, etc., and we'll reconvene in the hour. And we have some very exciting speakers and a very exciting panel that Isabel is organizing on which is very much connected to some of the last issues that Greg has raised on the overall impact of computing and even astronomy more broadly in terms of the resources being used and the impact on the climate. So thanks very much again to Greg and Bernhard for really exciting presentations, and see you in 25 minutes.
I sent you the slides, by the way, Ilya. Yeah.
Yep, I received them. I actually, Bernhard and Greg, if you don't mind, we have a website, and I can, if you don't mind your slides being as public as being put on the website, then rather than emailing them around, I could just put them on a website for this.
Yeah, that's so from my side, that's fine, because I've removed everything that may sort of belong to third parties apart from trivial images.
Cheers. Okay. Thanks, everyone.
Thanks. Take care.
Thank you.
See you in 25 minutes. Bye.